Hello, welcome back. Today we do generating functions, and this is going to be the penultimate lecture of your module 1 in terms of the syllabus that we are tracking. So typically whichever university you are from, generating functions, recurrence relations, etc. would all be a part of the first module. So that's what we are trying to track and complete. And after completing on the various kinds of searches and sorts and the complexities of that, which would be the next lecture in this series, we would start with module 2, which is going to be interesting in terms of cracking actual algorithms. So that being said, let's see what's in store for today in terms of generating functions. So this is typically something that I had observed that it's not explicitly mentioned in the syllabus, but it comes in coherence with recurrence relations, in coherence with substitutions methods, basically in coherence with solving of recurrence relations through, let's say, recurrence tree, substitution, Master Theorem. These are what we have already covered, and this generating function is the last way of solving it, and therefore it is not mentioned directly in your syllabus, but the questions and the patterns of discussions around what we have observed in your previous year's questionnaires from various university curriculums include it, which is why I'm trying to cover it as a part of this module. Now here what we'll discuss is we'll first discuss some preliminaries around partial fraction mathematics that will be required for solving this, and then we will get into the why generating function, why one more method, right? So that's something that we'll see, and then we'll solve one general generating function in terms of the solution that we want to build around it, and of course we will solve multiple other questionnaires that have come in your previous year questions. So that's something that we will track in terms of the agenda. So the first point that we are trying to see is some mathematics around, let's say, partial fraction decomposition. So what you see here is 7x minus 23, x square minus 7x plus 1. Now if such a partial fraction, or if such a fraction is given to you, can we solve it as a part of, or can we break it down as a part of partial fractions? Why is it required? It will be required when we try to solve the generating function way of doing time complexity calculations, right? So, and that's where I would need you to understand, in case you already don't know, how to solve or how to modulate this particular fractional equation into partial fractions, and then how to solve it. So let us see quickly how to solve this, and then you can understand when we start applying it to generating function, you can understand why it is or how it is being used, right? So we'll come to that as we cross the bridge. Now, what we'll say is, when I say partial fractions, what is partial fractions? So what I mean to say that this particular equation 7x plus 1 is actually writable in the format of a by, let's say, something plus b by something, right? So all of you need to understand that this is what the format I need. Can I convert my left hand side into something which is denoted by a in the numerator and something in the denominator, and then b in the numerator and something in the denominator, and we say that these are the additions of these two partial functions, right? So this is a partial function, and this is also a partial function. Both together make this, or partial fraction, my bad. This is a partial fraction, that is also a partial fraction. Both together make it as a partial fraction, right? So that's what we are trying to attempt to solve. Now, first of all, I hope you can understand that this particular right hand side will actually mean that we will, if I have to solve this, then I would be writing something like this. I would be writing, let's say, the LCM of the denominators, and then a will be multiplied by something to do the LCM justification, and b will be multiplied by something. So this together will be then representing 7x minus 23, and this LCM will be actually representing x square minus 7x plus 1. So that is what in the reverse sense will actually happen, right? So the way we will probably do it is to show you that the some things at the bottom will be simplified using an LCM, and then A can be multiplied and B can be multiplied to make them equal, and therefore what you will have at the numerator will be exactly the numerator of your LHS. What you will have at the denominator will be exactly the denominator of your LHS, right? So that's in a nutshell why we are doing this, or what is this partial function all about. Let me remove this and let me just start solving this for you. Okay, so let's solve the denominator portion. So let's solve this denominator portion here. So let's see that can I say that this implies 7x minus 23 divided by, now if I do the middle factorization of x squared minus 7x plus 1, then I will get x minus 5 and x minus 2. I'm not going to the details of this just to save time on this. So I'll be getting x minus 5 and x minus 2 when I do a middle term factorization of the denominator, right? So once you have done this, you can definitely say, okay, this got wiped out. Let me write this. So my goal is to write this in this format. So can I therefore say that this is going to be A by, now you know the something is x minus 5. I just now told you we are going to do the LCM. So when we do the LCM, we'll be multiplying the denominators. So it will be equal to the left hand side denominator, which is why I'm saying B by x minus 2. So if we do the LCM, the denominator will be the same as the denominator of the LHS. So that's where we can therefore say that we can represent the left hand side in this format of partial fractions. I hope you're understanding this. So now if we actually do the LCM of this, so we will get x minus 5, x minus 2, and then we will get A multiplied by x minus 2 plus B multiplied by x minus 5, and this will be equal to 7x minus 23, and here we will have x minus 5 and x minus 2. So we will therefore mean that this and this will go away, and we will be left with something like 7x minus 23 is equal to A into x minus 2 plus B into x minus 5, right? So that's what we will have. And then if we start solving the RHS, we will have AX minus A2, or let me write this as 2A, and we will have Bx minus 5B, which would also mean that if I group the x's terms, then I will have A plus Bx minus 2A minus 5B. Right now, if I compare the coefficients, so this A plus B is actually going to get compared with 7, because 7 has the factor of x here. We also have A plus B with x here. So I can write that my A plus B is equal to 7, and I can also write that minus 2A minus 5B is equal to minus 23, on the same logic that this entire stuff will be equal to this entire stuff, right? So these two will be equal, which is why I can write that if I compare the coefficients, A plus B equal to 7, A plus B will be equal to 7, minus 2A minus 5B will be equal to 23, right? So now if I just carry forward what we discovered in the previous slide so that we can solve this completely. So we said that A plus B is equal to 7, and then we said that minus 2A minus 5B is equal to minus 23. So this definitely implies that A is equal to 7 minus B, because this is what? This equation is 1, this equation is 2. So we have two equations, two variables. So it's a linear equation of two variables. So we have to solve for A and B, right? So that's what we are trying to do. So A is equal to 7 minus B. You can use any substitution method, you can use elimination method. I'm just doing a substitution method in terms of finding out A, which is 7 minus B, and then I will substitute. So this is, I'm saying 3, so I'm saying putting 3 into 2, right? So what do I get? Putting 3 into 2, I get minus 2, and then A is 7 minus B, so 7 minus B minus 5B equal to minus 23. This implies minus 14 plus 2b minus 5b is equal to minus 23. And this implies minus 14 plus 3b is equal to minus 23. And this implies that minus 3b is equal to minus 9, which implies that my b is equal to 3. So that's my b coming out from this. And similarly, we will also have that we knew that a is equal to 7 minus b, and if we substitute the value of b here, then a will become equal to 4. Right, so a will become equal to 4, and that's how we have solved this. So we can therefore write the equation as 7x. So we can write 7x minus 23 by x minus 5 and then x minus 2 as a partial fraction decomposition of 4 by x minus 5 plus 3 by x minus 2. So this is what you need to remember. This is what you need to solve when you start working with generating functions. You need to understand how to convert a complete fraction into partial fractions using the methodology that we have just now adopted. Right, so this is the mathematics prelude to getting into generating functions. Now, what is the necessity of generating functions is what we need to understand. Now, when we talk about generating functions, or rather before we talk about generating functions, we have done 2-3 things we have done. So we have done, let's say, one of the things we have done is recurrence tree. Okay, so we have done a recurrence tree method to solve recurrence relations. So what we are talking about? Actually, we are talking about solving recurrence relations, right? To find what? To find time complexity. So that is what we are talking about, solving recurrence relations to solve to find time complexities. Right, so this is what we are trying to find out. So if that is the case, that we have to solve recurrence relations, then the first method was recurrence tree. The second method was, let's say, substitution method. And if you don't know these, please visit my previous lectures. I've covered this in details. The second method is substitution method, and the third method, which was the most easiest of them all, was Master's Theorem. Right, so these are the things we have already covered, and this is what we actually use to solve recurrence relations in terms of finding out the time complexities. Right, now if I say that in the recurrence tree method, right, you typically will have let's say there will be a challenge, and I'll show you the challenges shortly, that this is not divide and conquer at all. In fact, let us try to aggregate these points against these values. So I am saying that this recurrence tree method of solving will have a challenge when the recurrence is not divide and conquer at all. Right? So there is no divide and conquer. That is, you do not have something like this Tn equal to Tn by 2. As soon as you do this, right, whatever constants you put here, this is dividing this particular bigger problem into sub-problems, and the sub-problem gets further divided. So therefore you are trying to solve smaller sub-problems in order to achieve the bigger solution, hence divide and conquer. Suppose this is not a divide and conquer problem at all, how does recurrence tree help them? So you'll see that there will be a challenge if this is not a symmetric divide and conquer problem. Right? Similarly, let's talk about the substitution method. Right? So the substitution method says that we substitute. Let's say we do the first level substitution, we do the second level substitution, we do the third level substitution, and then we find out the kth level substitution. Right? How do we find this out? This is called pattern matching. So we find out patterns from here, right? And then we decode a pattern which is applicable to my kth level. Suppose there is no pattern. Suppose you can't decode a pattern. Then what? Right? So this also creates a problem. So the no pattern available creates a problem in a substitution method kind of a solution. Master's Theorem also has a problem, because Master's Theorem has a set formula, right? And we'll discuss Master's Theorem where the problem can arise. So Master's Theorem cannot be applied if the function is not decreasing in nature. If the function is something like this, Tn is equal to Tn minus 1 plus 1, you cannot apply Master's theorem, because the function will not be decreasing nature. Or rather, let's put it like this: if it is Tn equal to let us say it is 2n, T2n plus 1, right? You cannot apply Master's theorem, right? So that's the reason, because Master's theorem, when we will discuss that in detail shortly, you will find out that there are some constraints of Master's theorem which you need to satisfy if you have to evaluate something through Master's theorem. So this is also going to be a challenge, and that's where you have the generating functions coming in to solve any and every problem, right? Forget about divide and conquer not available, so recurrence tree cannot solve it. Pattern is not discoverable, so substitution method cannot solve it. Master's theorem, those specific constraints are not applicable, so Master's theorem cannot solve it. But there will be generating function which will always be able to solve it, and that's why we are discussing that here. So I hope you are getting that point. Now let us see what are the specific problems with a recurrence tree. We will move into, I'll be shortly introduce you to the generating function, but first let us see the problems with the three methods, right? So this particular method, when we actually talk about let's say a recurrence relation which is Tn equal to Tn minus 1, Tn minus 2, if I quickly draw the tree, which will be looking like this, let's say Tn minus 2, and in this level it will further break down into Tn minus 2 and then Tn minus 3, and this will further break down into Tn minus 3 and Tn minus 4, and this will go on, right? So what can I see as the problems, right? I can see the problems as first problem I can see is Tn minus 2, it appears twice, right? So that I can see as a problem. I can see Tn minus 3 also appears twice, right? So these are appearing twice, which is complicating the per level work done. What is per level work done? This is my per level work done, right? So this is my work done that I typically would be doing in each level, right? So at this particular level, this is the work done. So what we want in a recurrence relation, let's see what all we want. We want that a recurrence relation should satisfy these three fundas. One, I should be able to calculate the work per level. Every level there will be a work done, and then I should know what is my number of levels, so that I can do this and this, multiply them together, right? So let me multiply these together. So then I will know the total work done per level, number of levels. You multiply it, you get the total work done, right? So that's what I need. And also what I need is this total work done I need in the form of a summation. So you remember, if you have seen my previous lectures, then we typically will multiply it, get a generic formula, and then do a summation so that we cover all the levels, and that's how we proceed. But if you see here, the problems that we have, the first problem was that we have repeated nodes. So if I explore this problem, we have repeated nodes, right? So we have repeated nodes means there is no clear work per level. So if I want to find out a pattern of the work per level, there is no clear work per level, right? So this work per level, there is nothing that is clear because it is getting repeated, right? So that's where we have a problem. Second problem that we have is the subtree sizes are different. Now why do I say that? Acha, if I say that when would this Tn minus 4 end? When would this Tn minus 3 end? When would this Tn minus 4 end? So of course this is getting reduced at a much faster rate than Tn minus 3. So if I say that this will end at T1, then for this T1 will occur here. For this is Tn minus 3, so it will end a bit farther. It will end probably here. This is also Tn minus 3, it will end probably here. And then this is the slowest, so it will end somewhere here, right? So these are the areas where your function will actually end. So this is a subtree. Let's say this subtree is ending at a different height this subtree is ending at a different height, this subtree, both these subtrees are ending at the same height, but these subtrees are ending at a different height as compared to the other subtrees. This subtree is also ending at a different height. So it makes the number of levels multiplication complicated. Just now I told you, right? If I know the work done at a particular level, multiply by the total number of levels. But the total number of levels here itself is long. Some subtree goes for x levels, some subtree goes for x plus y levels, some subtree goes for x plus y plus z levels. So how do you know total number of levels? You don't know. You'll have to add all the subtree levels and then multiply it with the work done at each level, right? So that complicates things, right? So that complicates things, and therefore my second problem that I'm seeing is that the subtree sizes are different. This is the second problem I'm seeing. And the third problem is that if I just look at it, deriving the formula, deriving the summation formula may be challenging at some points in times. So summation formula that we need to actually solve the problem is sometimes challenging. Sometimes challenging. Why? From a visual standpoint. So visually, if I examine the tree, sometimes we may not get to the substitution formula because of the complicated nature of the tree, right? So which is why in this linear reduction manner, this is basically linear reduction recurrence relation. If you don't know about it, watch my linear reduction recurrence relation video about it. So this linear reduction recurrence relation is going to create a problem from us from a recurrence tree standpoint to solve this. So recurrence tree always says, give me reducing or dividing kind of a problems, n by 2, n by 4, give me that kind of a problem. Don't give me n minus 1, n minus 2. Then my trees will look different. It will look staggered, it will look asymmetric, and the work per level cannot be done. Those are the problems that we have discussed in this particular scenario. Now there can be another problem from a recurrence tree. If suppose this equation is given, right? We don't have two recurrence or recursive calls like the previous one. If you see here, there were two recursive calls, right? Tn minus 1, Tn minus 2. Here we have only one recursive call. Now what's the problem with this? So if I convert this into a sigma notation, and if we do the recurrence tree, and I'm not going to do it, we have already done it in the previous lecture. Please watch the previous lecture. You will see that finally when the tree, from the tree, what we get is, this is what we get. We get that this will be sigma I 1 to n, and we get from the ith level that we say, we see that the work done is I. So for n levels, we will be doing sigma of I equal to 1 to n. For I, that is the work done at each level is I, there are n levels, so we'll do this, and then we have the base condition of theta 1, which gets added for the n minus 1 level. Right, so now this that we do, right, this entire thing that we do, to arrive at this, you need the help of the recurrence tree. You need the help of the recurrence tree to arrive at this. We have seen that at length. Please watch my recurrence tree videos around this. Now, if we arrive at this, and once we arrive at this, do I need recurrence tree? After this point, what do I need? After this point, I just need an algebraic solution. So who is going to help? How is recurrence tree going to help me? Nothing. Recurrence tree is not helping me to solve this. Right? So recurrence tree cannot go further beyond this. So I need one more method. What is that method? Algebraic method. So I will say that, okay, this particular situation is like this: 1 plus 2 plus 3 plus dot n, which actually evaluates to n into n plus 1 by 2, and therefore the dominant term here will be, so I can therefore write Tn as n into n plus 1 by 2 plus theta of 1, and here the dominant term is n square, so I can therefore write Tn as theta of n square. So this is what I would have written. What did I do here? I did simple algebra. Right, I did a simple algebra. Did recurrence tree help me? It didn't. Right, so recurrence tree cannot help you solve the problem completely. You are dependent on what? You are dependent on mathematics in order to solve the recurrence tree, and that is one more problem with recurrence trees. Right, so this is how your problems with recurrence trees will be there, and therefore if I take one more example just to explain to you another set of problems. See, this is, we are dividing. I just now said that recurrence tree is very happy when you divide it, n by 2, n by 4, but you are divided it in a jagged manner. right? N by 2 on one side, N by 3 on another side. So what do you get? You get something like, let's say Tn will divide to Tn by 2, and this will divide to Tn by 3, and this will divide to Tn by 4, and this will divide to Tn by 6, this will divide to Tn by 6, this will divide to Tn by 9, and this will go on. So who will end first? By 9 will end first. So suppose it ends here. This is T1. Who will end the next? Tn by 6 will end next. So this ends here. This is also ending here. And then finally this guy, which lasted the longest, will end. Right? Suppose it ends at T1. So this is how you are ending. So what are you getting? You are again getting what? A staggered tree. This is a one particular level. This subtree has X number of levels. This subtree has Y number of levels. This subtree has Z number of levels. All the levels here are not equal because this ends here. So the level will be smaller for this as compared to this, and that will be smaller as compared to this. So the levels of each subtree is different. So then the same problem comes, that how do you then multiply the work per level into the number of levels to get the total amount of summation work that you need to quote. And then we also have a sub problem. We have another problem, which is that the nodes are not equal. Right here, the nodes are not equal because the sub problem sizes are not the same. So I can therefore write that the nodes are not equal as the sub problem size is not the same. Now what do I mean by that? I mean that at the first level I have n by 2 and n by 3 as sub problem size. At the next level I have n by 4, n by 6, n by 6 and n by 9. So there is no parity in terms of how we are dividing the sub problems. On one hand we are saying one problem will be divided by 2, on the other hand we are saying another problem in the same level will be n by 3. Now that creates a jagged kind of a sub problems. Both the problems are not of the same size, right? And that is why we have nodes as unequal, and this is the reason why we say that the branches or the trees that we have are shrinking. The branches shrink at different speeds, right? So just now we have seen that branches shrink at different speeds. And therefore, if I say the work per level, let's see the work per level, is there some problem there also? So we have seen that the problem is that the nodes are not equal, sub problems are different. That creates a jagged tree. The jagged tree makes the branches shrink differently. So which is where I don't know the number of levels. I don't know the number of levels to multiply with my work per node or work per level, right? So let's see work per level also. Is that also a problem? Right, so work per level, first level is n, second level is n by 2 plus n by 3, which is 5n by 6. Third level is n by 4 plus n by 6 plus n by 6 plus n by 9, which is let's say if I do the LCM, it will come to 25n by 36. And this you will find the same example I've done in my previous lecture. You can find it down. So you see the work per level is also somewhat non-pattern discovery oriented, right? Immediately by seeing it, yes, you can find a pattern sometime, right? But then immediately on seeing it, you are unable to find a pattern. You'll have to rack your brains a few seconds or a few minutes in order to find the pattern. So that's where you are getting into a problematic scenario, that the recurrence tree is not helping you in this scenario to immediately get to a pattern, to immediately get to the total number of levels. Total number of levels is jagged, pattern is not coming out directly. The nodes are not equal, and hence that creates a problem for solving this particular recurrence relation using a recurrence tree method. So I hope you now understand that out of the three methods that we started, saying that we have understood these three methods, right? Here I had introduced those three methods to you. I had said that we have these three methods of solving, right? So these three methods, I have shown you recurrence tree, why I am saying it is a problem. Now let us see substitution method, why I am saying it is a problem, right? So let's go to substitution method. Now when I go to substitution method and when I take this, then my first substitution, I'll not do it cleanly in terms of the entire steps. I'll just show you abbreviatedly because anyway this is covered in the previous lecture. I'm just trying to show you the problem, okay? So the first substitution will lead to 2 to the power of 2 tn minus 2 Tn minus 2 plus 3. This is what the first substitution will lead to. You can do this problem, you will see that that's what you are getting. The second substitution will lead to 2 to the power of 3 Tn minus 3 plus 7. The third substitution will lead to 2 to the power of 4 Tn minus 4 plus 15. So can you guess the pattern of this? Can you guess the pattern of this? Because now you are supposed to take the kth substitution and find out a generic formula for this and a generic formula for this. If you don't understand this, watch my substitution method that I had followed for linear reduction and non-linear reduction recurrence relation, 2 lectures behind, right? So you will get to know what I am meaning from that. So kth substitution is what I need to find out. So I need to find out a general formula for this, a general formula for this, right? So the general formula I know. General formula is 2 to the power k t n minus k plus 2 to the power k minus 1, right? So this part can be easily guessed, right? This part can be easily guessed from the solutions that we are trying to attack, right? So actually this would be the second substitution. This will be the second substitution. First substitution is anyway what we start off with, right? So this is the second substitution, this is the third substitution, and this is the fourth substitution. We could have actually directly come from the third into the kth substitution, but let's say this is the fourth substitution. So then what you have is the kth substitution, which is 2k tn minus k plus this part. So this part was easy, right? We can easily discover that if this is the fourth substitution, this will be the kth substitution. I hope you can understand. 4 is here, 4 is here, 4 is here, so this becomes k. So this part is easy. What about this part? You don't know. Can you thump your chest and say that given 3, 7, 15 and given that this is second substitution, this is third substitution, this is fourth substitution, you can arrive at this formula, right? Directly, immediately, probably spending 30 seconds, 1 minute, 1.5 minutes, you may. Some may not, right? So the guessing of the pattern, for the kth substitution, is a big challenge, for substitution method, right? So guessing the pattern is a big challenge, which may or may not happen depending on the complexity of the recurrence relation, right? Hence, that's the problem with the substitution method that we will have to agree and warn ourselves against, right? So that therefore, let's move to the third method that we had learned, which was Master's Theorem. So let us say Master's Theorem is an excellent method. It can solve so many relations so quickly. But then what is the general formula for Master's Theorem? It is Tn equal to Atn by B plus Fn, right? And this is what we had learned. And then we also had said that the Master's Theorem, the recursive problem size should be n by b, and A should be greater than 1 and B should be greater than 1. A should be greater than equal to 1 and B should be greater than 1, not greater than equal to. So here, what is my A? My A is 2. 2 is greater than equal to 1. Okay, you are nice. You are good to go. What is my B? The B here, n minus 1, doesn't have a denominator. So if n minus 1 doesn't have a denominator, then what is my B? My B can be assumed to be 1. So B is equal to 1. Now B has to be greater than 1. So this is wrong. So this is wrong. This is wrong means this does not satisfy the template or the equation of Master's Theorem. So this cannot be solved using Master's Theorem, right? Because we have to have a reducing problem size. This is or a dividing problem size. We need to have a dividing problem rather than a linear reducing problem. So this is not a dividing problem, right? So this is not a dividing problem. Hence, we cannot solve it by Master's Theorem. Even if I put it in the form of the template, it is not satisfying B, and hence this cannot be solved by Master's Theorem. So if you see below, Master's Theorem cannot solve these particular problems. So I have already mentioned what all Master's Theorem cannot solve. Just have a look at this and you will understand that yes, this is of the format. This is because this is dividing. See, these two are all dividing. But whenever you have a linear reduction, this is not solvable. You have unequal shrink factors, not solvable. You have increasing problem size. Instead of dividing problem size, you are multiplying it by 2, not solvable. right? And then you have normal size, no shrinking is happening, n by 2 is not happening, not solvable. All of these, if you put A and B, you'll see it is violating. Either A is violating or B is violating or both are violating, right? And hence these are not solvable. So there are so many problems of Master's theorem that cannot be solved using so many problems of recurrence relations that cannot be solved using Master's theorem, right? So therefore, it makes it necessary to find out a generic function or generic method through which we can solve recurrence relations. So let me start introducing you to the generating function now that we have seen the problems. So introducing you to the generating function way of solving things. First, let's understand what's generating function. So let us take this equation, or rather recurrence function or recurrence relation, and let's try to solve it using substitution method. So I'll be quick in terms of solving it. The first substitution will actually result into this, and you can do it. I have done it already in the previous lecture. Please watch it out. This is after the first substitution, or rather we'll call it as the second substitution, because the first is the current substitution itself, current recurrence relation itself. So let's call it as the second substitution, and this second substitution, after being substituted third time, becomes like this: n minus 3 plus 1 plus 1 plus 1. This is my third substitution, right? So after the third substitution, this is what it will look like. What are we doing, or what did we do? Because in order to solve this Tn, we need to know Tn minus 1. So let's find out Tn minus 1. When you found out Tn minus 1, whatever you found out, put it inside this. So then you get this. That is your second substitution. So to solve this, you need Tn minus 2. So to find out Tn minus 2, again you solve for Tn minus 2. Whatever you get, you put it into this equation, you get this. That is your third. If you don't know the process, please visit my previous lecture. All I'm trying to say is that through substitution method, this is what you will get from a Tn perspective, right? So this is something that you will get, and at the end, eventually, what you will get is that this Tn will be equal to some T0 plus an n, because you see here this is n. This, when it goes to till n, right? When you keep on decreasing, finally n minus 3. This n minus 3, once you keep on decreasing, at some point will become 0, right? And when it becomes 0, you would have covered how many iterations of 1? You would have covered n times 1, right? So which is equal to n. So at Tn, we can definitely write T0 plus n, right? So that's how we have done it. Again, if you don't remember, you want to recollect, please go back and check the video regarding this in this playlist. So therefore, what we can say is that if I put T0 in place of n, if I put here T0, then what I will get is that I will be, or rather T0 will be already given for us. Let us not put here. T0 will be already given. So T0 will be given as 1. Let's assume T0 is given as 1 in this problem. So let's assume T0 here is given as 1. So therefore, if we put T0 as 1 here, then my Tn will be equal to n plus 1. So this becomes my generic answer to the solution of the recurrence relation, from which we can definitely get the dominating term as n. Therefore, Tn we can write in terms of time complexity as theta of n. So this is something we had already learned in the previous lecture. Right now, this Tn equal to n plus 1, can we somehow solve the entire sequence together without expanding one term at a time? That means we expanded first this term, then we expanded this term, then we expanded next term, then we calculated the last term. So each term we are expanding, then we are creating a summation equation, then we are solving it. So instead of solving each term, that means we don't know the next term, we are solving the next term, we don't know the next term, we are solving the next term, and in this way we are solving unknown terms. Instead of that, let us say, do we know that in this case T0 is equal to 1, T1 will be equal to 2, right? Just substitute for n is equal to 1, you will get, so if I substitute n equal to 1 here, I'll get T1 equal to 2. And then I can say that T2 will be equal to 3, T3 will be equal to 4, and so on and so forth, right? So every term I will get. So can I say that my sequence is actually 1, 2, 3, 4, 5 dot dot dot, right? So each term, that means when I say Tn, it is actually what? It is actually a recursive call n minus 1 times, right? N minus 1 is the sub-problem size, and we will make that recursive call till we reach the base condition. So that first call is let's say Tn. The second call is Tn minus 1. In this way, right? So can I therefore say that let's say my call number is actually called as index, and the value that I get at that index is what I have already got here. So how is this 1 going to come out? This 1 is going to come from where? At T0, right? When does T0 happen? So first imagine this Tn minus 1 started with Tn minus 1, then it became Tn minus 2, then it became Tn minus 3, then it became T0 finally, right? So at the 0th index, if I consider the last index as the 0th index, right? If I consider the last index as the 0th index, I am getting a value of 1. So just before that index, if I consider, so 0th index I am getting 1, the 1th index I will get what? 2, right? So this is my last index, this is my last index, this is my T0, right? I told you here that we are reaching T0 at the end, then just before it we would have T1, right? So at the T1th index our value should have been 2, right? At the T1th index our value should have been 2, right? At the T2th index our value should have been 3. At the T3th index our value should have been 4, right? So this is what we are actually getting from here, right? This is what we are actually getting from here. 1, 2, 3, 4 as my what? As my work done, right? So we are getting this as my work done. So I hope you have understood that when we go down this chain, at some point we will be reaching 0. At that 0th point, I have already calculated that my complexity is or my time taken is coming to be 1 unit of time. Then at the 1th position, that is just before this Tn, if I take this particular thing, then I will get the 2 as my time taken, right? So that way I wanted to make you understand that this T0 that is here, right? This T0 represents what? Represents if n is 0, then what is going to be my work done? What is going to be the time taken to get the work done? Then if n is 1, what is going to be the time taken to get this work done? So basically, if you think about it, if n is 1, n is 2, n is 3, n is 4, then you are actually going up here. You are increasing the value of n as you go up, right? So at each level, some amount of work is getting done, and that's what we are capturing. When n is 0, that means we are here, right? Some amount of work has been done. At n equal to 1, some amount of work has been done. At n equal to 2, some amount of work will be done, right? So that is how we are actually classifying this, by saying that these are my levels, or these are the n values, right? And this is the amount of work that is done, and that's clearly apparent from here. So I hope this part, I hope you are able to understand that this sequence that we have established is not just sufficient, because we also need to maintain the fact that this 1 comes from T0, this 2 comes from T1, this 3 comes from T2, and this 4 comes from T4, right? We have to maintain that sequence. So the recurrence definitely produces a sequence. So I have to say that this is how it looks like. We have first T0, next time we run, we will get T0 plus T1x, right? So we are combining whatever we are getting in the form of multiplying it by x, so that this index position is maintained. So can I say this is x to the power of 0? Can I say this is x to the power of 1? So T0 multiplied by x to the power of 0, just to retain the position that it occurs in, right? I'm just trying to retain. So T0 is what? T0 is 1. But where does it occur? At a position of 0. That means it occurs because of T0. How do I maintain that? The value is 1. From 1 I cannot know T0, right? T0 is 1. If I know this, can I know this? No. So how do I maintain this 0? I multiply it with x and put a coefficient of 0, right? The next one is something like this, T1 of x to the power of 1. The next one is going to look like this, T0 of x to the power of 0 plus T1 of x to the power of 1 plus t2 of x to the power of 2. So can I generalize this by saying that I will create a function called gx, which is called the generating function, which will look like this: t0 plus t1x plus t2x square, and so on. Yes, I can, because this is going to be my generating function. So what did I do? I just said that instead of finding out each level, that is, instead of finding out what you don't know n minus 1, so you find out n minus 1. You don't know n minus 2, you find out n minus 2, and so on and so forth. Instead of finding out each level, can I flatten it out? Can I flatten it out and say that gx comprises of all of this? So I'm going from an unknown area to a known area, and this is more mathematical or algebraic in nature rather than recurrence in nature, right? So where am I going? I'm going towards the fact that gx is actually a summation of t0, t1, t2, right? So this is where I'm saying that imagine this tn minus 1 to be comprising of all of this, right? And I'm saying that if I can create a flattened algebraic expression of all those smaller things that we don't know, then I create something called as a generating function, right? So that's where the definition of generating function comes from. The recurrence relation has now become an algebraic relation. The recurrence relation is now algebraically formed. There is no recurrence relation here. Can you find any call for tn? Do you see any tn? Do you see any tn by 2? Do you see any tn minus 1? Do you see any of these? You don't see any of these. Where? Here. You don't see any of these here, which means it's no more a recurrence relation. It's now become a mathematical relation, right? So if you know t0, t1, t2, etc., you can solve it. Just substitute the value of t0, t1, t2, you'll get it. In the earlier case, we had to do what? We had to solve for the recurrence relation, or we had to solve for this tn minus 2, which was a recurrence relation. So tn minus 2 leaded to tn minus 3. Tn minus 3 says, I don't know, I can only know myself. You call tn minus 4. So it was going through a recurrence relation format. Here I don't have a problem now. If I know t0, t1, t2, I have my solutions. There is no recurrence call here. There is no tn. There is no factor of tn. I hope you can understand where I am getting at. So instead of expanding the results repeatedly, we are manipulating one algebraic object. This is that one algebraic object. So we have to just solve this algebraic object. Instead of going through each and every tn minus 1, solve it, tn minus 2, solve it. Instead of going through all of that painful process, solve for this algebraic object. That is what we are trying to see. So we can, in mathematical terms, so let us use a fresh page. So if we just now saw that my gx is equal to what? My gx is equal to t0 plus t1 x plus t2 x square plus dot dot dot. Now algebraically we can, or it is written in mathematics, sequences are written as a0, a1, a2 dot dot dot. So we will substitute our gx wherever we see t0, we substitute by a0. We can put an x0 if we want. Then we will say this will be a1 x1, right? So we will say a1 x1, then we will say a2 x2, and so on and so forth. Therefore the general term, so this at the kth iteration, so this will go till k, right? Somewhere this will reach k. At that kth value, what we will get? We will get ak xk, right? Easy to understand. At the kth value, we will get ak sk. Then this will be a summation of ak xk. So gx can be written as a summation of, let's say, k equal to 0 to infinity. Why? Because see, here it is 0 and then it goes to infinity, because we don't know where it will stop, and this will be ak xk, right? So this is what I wanted to show you, that this is the general form of a recurrence relation. So this is our equation form of recurrence relation, and if we convert it into a general form, then we are going to get this as ak xk, and therefore the general form will look like this. So this will be your general form of the recurrence relation. So that is in a nutshell what a recurrence relation, generating function is all about. If I've said recurrence relation, it's actually the way to write the recurrence relation as a generating function. We have still not solved the recurrence relation, right? Our main goal was what? Our main goal was there is a recurrence relation, right? We have three ways to solve it. We have understood a recurrence tree method, we have understood substitution method, we have understood Master's Theorem method, right? And none of these ways are helping us solve all kinds of recurrence relation. So in comes our fourth type, which we are calling as generating function. So this has to solve the complexity. So at the end of the day, I need the complexity, right? I have not arrived at the complexity. All I said is this recurrence relation, I'm going to express this recurrence relation. I'm going to express this recurrence relation. 1 minute. Yeah. So I'm going to express this recurrence relation as a generating function first. So I have expressed this as a generating function. This is the general form of the generating function. This is the expanded form of the generating function. And again, let me summarize. Generating function is what? It is basically, if I go back here, it is basically avoiding calculating all these individual recurrence relations, and instead finding out an algebraic way to figure out an equation with which we can represent that particular recurrence relation. So this same recurrence relation is represented like this, right? Instead of having the n-1, n-2, n-3 in its equation, right? We are eliminating n from the scenario. We are eliminating tn-1 or tn by 2 or tn or whatever that factor of tn is, and we are putting it as a more of a some kind of a constant terms, that if we know these constant terms, we can calculate gx, which is our output of this tn, right? Without even relying on finding tn-1, tn-2, tn-3 and so on and so forth, substituting it back to back, right? We don't care about that. So that is where we are doing an algebraic solution of an algebraic object. That is what is generating function. And then we saw that the general form of the generating function is like this, and then we saw that we have to maintain the positions here, and we have to maintain the coefficients, which are the values of t0, t1, tn, etc., etc. And then we saw that we can definitely represent it as a what? As a summation of ak xk, right? So this is what we have learned from a generating function standpoint. Now let us say that let us take a relation. Okay, let's say that there are certain things you need to also know about generating functions. You now know what is a generating function, how does it look like, why do you need a generating function. Those parts we have covered. Now at some point when you start solving generating functions, we will go to the solution, don't worry. There will be a necessity to understand this problem, whatever we are discussing right now. Let us say the sequence is 1, 2, 3, 4. When I say sequence, what is the sequence? The sequence is, if you see here, we had generated a sequence. Right here we had generated this sequence. This is t0, t1, t2, t3. The values are actually the sequence. This is my sequence. Right? If you put t0, that is t, if you put n as 0, n as 1, n as 2, right? What does your tn become? Those tn's, as you increasingly put the n's, that is n equal to 1, 2, 3, 4, you get some values of tn, right? And if you put those in sequence, then you get something called as what we are calling as sequence here, 1, 2, 3, 4, 5. Let us say that we have a sequence 1, 2, 3, 4, 5. Right? Let us say we have a sequence of 1, 2, 3, 4, 5. That is t0 is 1, t1 is 2, and so on and so forth. Right? I hope you all are understanding this. So my generating function, which I know gx is actually a0 plus a1x plus a2x square plus dot dot dot. This is my general format of generating function. Can I write this as a0? See, a0 is 1. If the sequence is 1, 2, 3, 4, 5, then 1 must have come from t0. Right? So my a0 has to be 1. My a0 has to be, what is A0? A0 is nothing but T0. And I said T0 is 1. So A0 has to be 1. A1 has to be T1. Right? A1 has to be T1 and A1 is 2. So T1 contributes to 2. What is the value? The value is what the coefficients are. Right? In the sequence, whatever the value is becomes the coefficients. So A0 is the coefficient of finding it out from T0. A1 is the coefficient of finding out from T1. That's why if I know that this 1 is generated from A0, this 2 is generated from A1, I will put those coefficients here. I will put those coefficients here like this. Right? Now, we know that, let us say, in fact, the sequence is not 1, 2, 3, 4, 5. I started off with a wrong sequence. This is the second part of the problem. So when I go here, we will be covering this sequence 1, 2, 3, 4. I accidentally moved into this particular topic. I thought this was, I didn't notice that this was the 1, 1, 1, 1 sequence. Right? The 1, 1, 1, 1 sequence is what we have solved here. Let me show you what we have solved here. The 1, 1, 1, 1 sequence. Yeah, so this is not the 1, 1, 1, 1 sequence. This is the 1, 2, 3, 4, 5 sequence, as I told you, right? And we were trying to solve the second part of the slide that you saw. We'll go there, right? We will go there. We'll again repeat whatever we have done. But for now, what I'm trying to say is, let us say that your function has been solved as this. Let us say that your function has been solved as this. Yeah. So let us say that your function has a sequence of this. So what does this mean? This means my T0 is actually 1. My T1 is also 1. My T2 is also 1. So this is what this means. This means that the sequence getting generated is always 1 whenever you put the value of n as increasing order. Therefore, can I write my Gx as, what is Gx? A0, A1x, A2x square, A3x cube. You know by now, right? We have discussed this. Now, if I put A0 as T0, then this becomes 1. A1 as T1, then this becomes 1. So everywhere the value is 1. So I'm putting 1 every coefficient, right? So 1x plus 1x square plus 1x cube, right? So can I write this as this 1 plus x square plus x cube plus dot dot dot. What is this? This is GP. This is a GP with first term which is a equal to 1, and the common ratio for this GP is r equal to x. So we know that the GP that is here, we will write this as therefore the summation of this particular thing. If I just put that Gx, the Gx will be 1 by 1 minus r, right? From the GP formula with a equal to 1 and r equal to x, you can write it as 1 by 1 minus r, because r equal to x, right? So in that sense, I can actually put this as 1 by 1 minus x also. So Gx, the generating function, will become 1 by 1 minus x when the sequence is 1, 1, 1, 1, 1, 1. That is, when T0 becomes 1, T1 becomes 1, T2 becomes 1. In such a case, if you find that the recurrence relation is going towards that scenario, then the generating function that will eliminate the Tn's, Tn minus 1, Tn minus 2, that generating function will be written as 1 by 1 minus x. Right, so that is one part of this particular solution, and this is what we had already started. We had said that if T0 produces 1, if T1 produces 2, if T2 produces 3, and so on and so forth, right? Can I therefore say that if my Gx is written as A0 plus A1x plus A2x square plus dot dot dot, then Gx can be actually written as, I'll substitute the T0 value, right? 0th value will go into A0, which is 1, plus T1 is 2, so 2x plus 3x square, and so on and so forth. And we know just now we have seen 1 by 1 minus x is equal to 1 plus x square plus x cube. right? So can I take a differentiation of both sides? I hope you remember differentiation. So this means that this is 1 into 1 minus x to the power of minus 1. So I can write this as 1 minus x to the power of minus 1 LHS, and that is equal to 1 plus x square plus x cube. So if I use the chain rule of differentiation and I put a ddx of, so let's say my left hand side is, I'm doing a differentiation on both sides. So if I do a differentiation on the left hand side, I would be getting something like this, 1 minus x square, right? So that's my ddx on the left hand side. For my right hand side, if I do a ddx of 1 plus I will do a ddx of x plus I will do a ddx of x square, and in this way it will go on, right? So ddx of 1 is a constant, so it becomes 0. ddx of x is 1, ddx of x square is 2. And then I go inside x, and ddx of x is x. So that way what I'm getting is 0 plus 1 plus 2x plus 3x square plus 4x cube. This is what I will be getting. So I can therefore write that 1 by 1 minus x square is equal to 1 plus 2x plus 3x square plus 4x cube, and so on and so forth. And what is this? If you see here, this is your gx. Just see your gx, what we started off with. We had started off with gx as 1 plus 2x plus 3x square. Don't you think this is the same as this? Right? So of course it is the same as this. So therefore I can say that 1 by 1 minus x whole square is equal to my gx. So that is what we have written here. Your generating function will be equal to 1 by 1 minus x square when the sequence that comes out from t0 is 1, t1 is 2, t2 is 3, sequence that comes out is 1, 2, 3, 4, 5. Then the generating function, when you solve the generating function, you will be using this formula that gx will be equal to 1 by 1 minus x square. So similarly, there are other kinds of scenarios that you will get, right? So we have said that gx, we know this. I hope you remember that we had said my general formula for the generating function is gx is equal to sigma of n equal to 0 to infinity a n xn. We had established this where? We had established this here. This is where we had established it. Right here, this is k, I've taken there n, it's all the same. So I hope you remember this. Now I'm saying that if the sequence is 1, that is all ones, then just now we have seen that we can use the generating function formula as 1 by 1 minus x. If the sequence is k plus 1 or n plus 1, right? If the sequence is n plus 1, which means that the sequence n's value is 0, then n plus 1 becomes 1, n's value is 1, then n plus 1 becomes 2, and so on, right? We have seen this also. We have seen this also, saying that the value of this will be 1 by 1 minus x square. And likewise, you will see that there are other recurrence relations where the value of n is just n. That means first it will be 0, 1, because n moves from 0, right? So 0, 1, 2, 3. If this is the format, then also we get x, then also no, I'm sorry for that, we don't get this 1 at the top, we get x at the top, right? The numerator remains the same. And then if we have a to the power of n, then the first value is a to the power of 0, which is 1, second value is a to the power of 1, and so on. Then your generating function will actually take the shape of 1 by 1 minus ax. Now we'll not go into the details of proving this. I just gave you two proofs just to make sure you understand why I'm saying that this becomes equal to this. So what is the logic? Similar logics will be applied here, and this table is for you to remember, right? So with this, let me move on to the actual methodology of solving the recurrence relation. And now that you have understood everything about generating functions and solutions of recurrence relation using generating functions, why we use generating functions, what are the problems with recurrence tree, substitution method, Master's theorem, what is generating function, how to derive it, what is the general format of it, and what are the intermediate solutions that you can apply through that table, right? Now we are in a shape to solve recurrence relations using generating functions. Okay, so the generating function looks like this. And don't get worried about this, or don't get too hung up about this. this is nothing but Tn plus 2 minus 3 Tn plus 1 plus 2 Tn. So when you put it in generating function format, it's no more written as Tn, it's typically written as An, right? So that is where this An format is coming, right? So don't worry about the format. Now, if this is my generating function, it is saying that solve the recurrence relation. So actually the solution to this recurrence relation is something there, because it wants you to solve it using generating functions. So the recurrence relation is itself written like this. The recurrence relation is not written in the format of Tn plus 2 or Tn plus 1, but internally you would know that Tn plus 2 is An plus 2, Tn plus 1 is An plus 1, right? So ultimately, what is the recurrence relation? Tn plus 2 minus 3 Tn plus 1 plus 2 Tn is equal to 0, with T0 equal to 2 and T1 equal to 3. This is what is given. This is what a recurrence relation, na? Tn plus 2 minus 3 Tn plus 2 and Tn equal to 0. Why don't you recognize this? You don't recognize this because it is written all in one shot. If I would have put it like this, 2 Tn is equal to 3 Tn plus 1 minus Tn plus 2. I just rearrange the terms. Now you recognize it. 2 Tn equal to 3 Tn plus 1 minus Tn plus 2. So this is a recurrence relation. To solve Tn, you need to know n plus 1. You need to know n plus 2, the smaller problems, right? So that is where this is our recurrence relation. And this recurrence relation, you will face a lot of difficulty to solve using recurrence tree. You will face a lot of difficulty to solve it using substitution method as well as Master's theorem, which is why you need generating functions, right? So we'll have to find out the generating function for this recurrence relation. So step 1 is find the generating function for this recurrence relation. Step 2 is solve the generating function. To find what? Step 3, the complexity. At the end of the day, we have to find, don't forget, theta. Theta of what? We have to find Tn, the asymptotic complexity, as in terms of theta, right? Tn is equal to theta of what? That is what we have to find out, right? So we need to first find out what is the generating function for this. So what we'll do is, we will multiply the equation, this same equation we will multiply with x to the power of n. Acha, by the way, one more important thing is, what is the lowest suffix of n? The lowest suffix of n is n here, because this is n plus 1 higher than n, this is n plus 2 higher than n. So the lowest suffix of n is n. Now if you put a equal to 0, that means you are putting n equal to 0, right? A0 means this n, the lowest suffix, will be equal to 0, right? Therefore we will use this, the starting point of n is 0 and it will go till infinity, and I'm telling you why. So we will say that typically what will happen is we will say that we are going to do a mathematical solution for this. As I said, we are not going to do recurrence based solution. We will create a generating function which will be an algebraic solution, right, instead of solving it in a recurrence manner. So we will say that we will multiply with x to the power of n and sum from 0 to infinity. Why 0? Because I found that this is 0, right? I found that a0 is given and I found the lowest suffix as n, therefore n has to be 0. So I start from 0, I move to infinity. After I multiply things by x to the power of n. So the equation will look like this: summation sigma of n equal to 0 to infinity. The first term a n plus 2 I will write as is, and I have multiplied it by x to the power of n, right? The second term will be minus 3 sigma n equal to 0 to infinity of a n plus 1, and then we will multiply it by x to the power of n. Everywhere we are multiplying by x to the power of n. Then we will say n equal to 0 to infinity of a to the power of n x to the power of n equal to 0. So this is what my equation comes to. Now if I expand this, what I am getting is that if I put n equal to 0, suppose I have put n equal to 0 here, then what will this term be? A2 x0. This will be A3 x1. This will be A4 x2. Right? So if I just expand these, right? I'm sorry for that. This is not A3x the way I mentioned, and this is also not A4x square. A3x is here only, right? So think about it. N equal to 0 means this becomes A2 x to the power 0. The next time it comes, that is n becomes 1, then this becomes A3x. The next time n comes, which is n equal to 2, this becomes A4 x square. So this term, if you expand, right, let me write down. So this term, if you expand, it becomes equal to A2 plus A3 x. A3 has to be a suffix. A2 also has to be a suffix. So A2, A3, A4 x square plus this. So I have expanded this term like this. So if I expand the next term, then this will be, let's see what expansion it comes to. N equal to 0. If I put n equal to 0 here, this becomes A1. This becomes x to the power 0. So A1 x to the power of 0. A2 x to the power of 1. A3 x to the power of 2. Right? So let's put that. So this becomes 3 A1 plus A2 x plus A3 x square plus dot dot dot. What happens to this term? So this is my output from this term. What happens to this term? So here, if I put A0, then this also becomes x0. So this is A0 plus A1x plus A2x square and so on and so forth. So which will have that 2 A0 plus A1x plus A2 x square. Again, I'm putting it in the power, my bad. X square. Okay, that was okay. X square is okay. That power is okay. A1x. So this is not right. My coefficient suffix should not go to the power. Right? My coefficient suffix should not go to the power. So this will be A0. This will be A1x. This will be A2x square and so on, which is equal to 0. So that's what you get from this particular equation. So we are just taking this equation. I'm treating this as a mathematical equation. I'm just using mathematics now. I have not even done any recurrence. All I said is I'll multiply it by x to the power of n and I'll sum it up from n equal to 0 to infinity. That's all I said. There is nothing to do with recurrence relations here. So now let me put the general equation. Let me go this side. Right, so I'm going to this side now. Okay, so from here, if I write my general equation is gx is equal to a0 a1x plus a2x square plus dot dot dot. This you know. This is the generating function. What am I going to? I'm taking the, I started with this recurrence relation. So this is the recurrence relation with which I started. Right, so this one. This is the recurrence relation with which I started. And I want to get to this format. What is this? This is my generating function. Why? Think about the steps I've written here. The step says from this equation, which is the recurrence relation, find out the generating function. So I'm now moving to that stage that I'm trying to find out the generating function gx. Right, so let us find out the generating function. So we have to manipulate the equation that we have here, right, in this format. We have to manipulate and then we'll get the coefficients of a0, a1, a2, etc. So let's start the manipulation process. So let's take the first term. Right, so the first term for us is, if I see here, this is my first term. Right, so I will take the first term. So first term is a2 plus a3x plus a4x square. Now you start comparing this first term with the general function. This with this. What do you see? You see that a2, see a2 should come with x square. X square is missing here. a3 should come with x cube. So x square is again missing here. a4 should come with x4. So x square is again missing here. So immediately you realize that throughout I have to multiply by x square. Right? So in order to make this the same, what I will say is that this can be written as a2 x square, a3 x cube, a4 x4, and I will also have to divide it by x square to keep the numerator denominator the same. Right? So x square will cancel out, and hence we will get back our original term. So all I did is at the numerator and the denominator I multiplied by x square. Why? Because I wanted it to come in this format. a2x square, a2x square has come. a3x cube has come. a4x4 has come. Right? Now if you observe that if I just take this equation, okay, just take this equation and bring a0 and a1x to the left. Just bring a0 and a1x to the left. So your gx minus a0 minus a1x becomes equal to a2x square plus a3x cube plus dot dot dot. Why did I do it? Because this particular term starts from a2. I want my generating function also to start from a2, which means I have to take these terms to the left hand side of this particular equation. So my gx minus a0 minus a1x is nothing but this. So therefore, can I therefore write my first term as equal to gx. See, this part of the problem a2x square etc. is like this. So it is actually equal to this. So let me put it here. Right, so let's say that this becomes gx minus a0 minus a1x, because that is what is a2x square plus a3x, and we had found out this is the numerator of the first term. So divided by x square. So this is my first term. So likewise, let us solve for the second term also. So let's write the second term. My second term is like this. My second term is a1 plus a2x plus a3x square plus dot dot dot. Right? So again, if we are comparing it with gx, then gx is a0, a1x, a2x square, a3x cube. So what are we missing here? Just see here. a1 comes with x, so x is missing. a2 comes with x square. Sorry, a2 comes with x square, because a2 comes with x square, but here a2 has x, so x is missing here. a3 comes with x cube, x is missing here. So of course you realize now that you have to multiply the second term with the multiplication has to be done with x. So when you multiply, this becomes a1x, a2x square, a3x cube dot dot dot, and you have to also divide by x in order to keep it the same. And when you compare this with this, you see that this part of the problem of gx is the same, but this part of the problem of gx is the same. So you have to eliminate this a0, take it to the left side. So now take gx and say that gx minus a0 is equal to a1x plus a2x square plus a3x cube plus dot dot dot. Right? So that's what you do, and therefore now you can write your second term as equal to because now you have a reason to say that this entire thing is this thing. Right? So you can definitely now write the second term as gx minus a0 divided by x. Right? So you can write this as gx minus a0 divided by x. So what will be your third term? The third term is actually already equal to gx, because the third term is a0 a1x plus a2x square plus dot dot dot. If you go back and see the third term, this is what the third term is, a0 a1x a2x square. This is what the third term is, which is already in the format of gx. So now if I take the entire equation, then my equation now becomes, let me put the equation in this side. So my equation now becomes, if you see here in the previous slide, those terms had some coefficients, right? So those terms had some coefficients. Here there was a coefficient of -3, here there was a coefficient of +2. Well, we'll have to put those coefficients and adjust the terms. So if we do that, we are going to get gx minus a0 minus a1x, which was my first term, divided by x squared. This was my first term. There is no coefficient here. Second term had a coefficient of -3, and the second term we had solved it as gx minus a0 by x, and the third term we know is with the coefficient of this we get gx. So this is what I get. Now you are already given the values, right? You are already given the values of a0 equal to 2, a0 equal to 2, a1 equal to 3. So substitute them here, right? So then we are going to get gx gx minus 2, a0 equal to 2, and this is equal to 3. So gx minus 2 minus 3x by x square minus 3 gx minus 2 by x plus 2 gx. This is equal to 0. So now you solve this. If you solve this, then we'll do a LCM. So x square will be multiplied all throughout. So we will have gx minus 2 minus 3x, right, minus 3 x because of the LCM, and then gx minus 2 plus 2x square gx, which will be equal to 0. X square will go to the other side, get multiplied by 0 and get cancelled out, right? So that's and then if we expand this, then we will get that gx minus 2 minus 3x minus 3x gx plus 6x plus 2x square gx is equal to 0. So if we group the gx terms, then what we are going to get? We are going to get gx, and then we take a common, so it is 1 minus 3x plus 2x square, and then the rest of the terms is like looking like this, minus 2 plus 3x equal to 0. Therefore we can say that gx is equal to, or gx multiplied by 1 minus 3x plus 2x square is equal to, if I take it to the other side, it becomes, sign changes, 2 minus 3x. Now I can write my gx as gx is equal to 2 minus 3x divided by 1 minus 3x plus 2x square. So finally we have a problem like a mixed fraction. If you remember, I had given this in the beginning of this lecture, that if you have a problem like this, how can you convert it into a partial fraction, right? How can you decompose it into a partial fraction? So we will decompose this gx into a partial fraction now. So let us take the decomposition here. So if we factor out the denominator, so let me write this here again for your reference. So we are saying that we had got gx as 2 minus 3x divided by 1 minus 3x plus 2x square, right? So if we factor the denominator, then we will get that 2 minus 3x gx is equal to 2 minus 3x divided by, factoring the denominator, I will get 1 minus x and 1 minus 2x, middle term factorization. And I can therefore write this, I have already taught you how to do it, that we can therefore write this as a sum of partial fractions, right? So I can solve this now. I can say that if I take the LCM, then this would imply that 2 minus 3x is equal to a into 1 minus 2x plus b into 1 minus x. So if we expand this now, we will see that 2 minus 3x is equal to a minus 2ax plus b minus bx, which implies this is equal to, if I take a and b together, then it will be plus minus 2a minus b into x. Now if I compare the coefficients on the left side with the right side, then a plus b is equal to 2 and minus 2a minus b is equal to 3. Right, so that's how the partial fraction is helping you, and if we solve this, then we will get a equal to 1, b equal to 1. Therefore, you can write your generating function gx as 1 by 1 minus x plus 1 by 1 minus 2x. from here, right? So from here you can use that and use these two that you found out to actually write this. So now you see what has happened. We started off from a recurrence relation, we ended up with a generating function which does not have anything to do with what? Tn minus 1 or an minus 2. The recurrence relation had this, na? It had an minus 2, an plus 2, an plus 1, an, and we have eliminated that because those were recursive calls, right? So we have eliminated that and we have reached into a situation where we are saying it is more of an algebraic nature. Gx is now algebraic. Solve this algebraically, you will get your problem. You will get the answer to the problem. So you have already seen, right, from this table, you have already seen that 1 by 1 minus x in a generating function is to be treated as a sequence of ones. So this is what it is, as a sequence of ones. If your generating function actually takes 1 by 1 minus x, then the sequence is actually 1 1 1 1 1 1 1, right? So that's what we had seen. So similarly here, if my generating function is 1 by 1 minus x, I can take this as a sequence of 1 1 1 1 1. So what is this 1 1 1 1 1, by the way? So if you see here, this is what an is. If you see here, this is what an is. So this is 1. This is 1. So if an is 1, so here my an is equal to 1. Right? So then my sigma will look like this, x to the power of n equal to 0 to infinity. So this is what it will look like, my sigma, an equal to 1. Therefore, the gx will actually look like sigma of n equal to 0 to infinity of x to the power of n. Right? X to the power of n. That's what it will look like. Right? So can I put this here? So let me put this here. So 1 by 1 minus x. Yeah. So 1 by 1 minus x will look like this. One by 1 minus x is equal to sigma n equal to 0 to infinity of x to the power of n. Just now from the table we have found out. Right? What is the next one? 1 minus 2x. So 1 by 1 minus 2x. Now what is this from the table? Let's go to the table. Right? So 1 minus 2x is falling under this, where a equal to 2. Right? So where a equal to 2. So can I write this? A is equal to 2 here, which means that this will be sigma n equal to 0 to infinity, and my an remains as an. So this becomes, because a is 2 here, so 2 to the power of n, x to the power of n. Because a is 2, 1 by 1 minus 2x, right, is what you got. 1 by 1 minus 2x is what you got. Right? So if you got that, then on the left side I can easily write down that this will be of this format. An will be actually 2n, right? So 2n x to the power of n. So that will be my generating function, right? So this will be 2n x to the power of n. Now if I go here, then I can write this down as 1 by 1 minus 2x is equal to sigma n equal to 0 to infinity 2 to the power of n x to the power of n, which implies I can write my gx as sigma n equal to 0 to infinity of x to the power of n plus sigma n equal to 0 to infinity of 2 to the power of n x to the power of n. Right? So I can write this as this. So if I write this as this, then I can put an overall sigma from n equal to 0 to infinity, and I can say that 1 plus, if I take x to the power of n common, I can write this as like this. I just took x to the power of n common. So now if I compare it with the coefficients of x to the power of n, right? So if I compare it with the coefficients, what do I know? That my gx, your generic form of gx is what? Gx is equal to a to the power of n, x to the power of n, right? So this is my gx. In fact, this is sigma of n equal to 0 to infinity. This is what we know. Therefore, I can say that my an is equal to 1 plus 2 to the power of n. Why? Because I just compared this with this equation, and this equation is actually of this format, right? This equation is actually of this format, an xn, and that's why I can write this as an equal to 1 plus 2 to the power of n by comparing the coefficients. And this is your solution of the recurrence relation through generating function. But this is not your time complexity. So my time complexity is an, or you can write this as Tn, right? Anyone you can write, which is theta of 2 to the power of n, because that is your dominant term. So this is my time complexity of the recurrence relation that was supplied to me. I found this out through my recurrence generating function method. So this is how you find it. It's a bit lengthy. If it comes, it will come for 10 or 15 marks, right? So that's something which is very scoring, but at the same time you'll have to understand the process involved, right? So that's on this particular solution of generating function. So let's move on to the previous year questions and see what kind of questions have come around this. So typically, let's take the first typical question that is asked. It's mostly similar to what we did. It's just that it's going to be lengthy, but let's do it anyways, because anyways you never know what comes out of it. So this is what the function is, the recurrence relation is rather. So again we'll do the same thing. We'll find the generating function first, and then we'll solve the generating function to find out the time complexity. Right, so let us do that step by step. So we'll rewrite this recurrence relation as I'll just take everything on the same side. So we will say an minus 6a n minus 1 plus 11a n minus 2 minus 6a n minus 3 is equal to 0. I just wrote everything on the same side. And now what is given? So you see here, I told you, you take the lowest suffix. So lowest suffix is n minus 3, right? And you have a0. So this lowest suffix n minus 3 has to be equal to 0, which means that n has to be equal to 3. So when you take the sigma, you will start n from 3 to infinity instead of 0 to infinity, right? So that's why this is important. So now if we start solving this, we will say that we'll multiply left and right side with x to the power of n. So let me write this down. Multiplying with x to the power of n and summing it from 3 to infinity. What do we get? We get sigma n equal to 3 to infinity of an xn minus 6 sigma n equal to 3 to infinity of an minus 1 xn plus 11 sigma n equal to 3 to infinity of an minus 2 xn minus 6 sigma n equal to 3 to infinity of an minus 3 xn, and this is equal to 0. This is equal to 0. So this, what I did, just multiplied it by x to the power of n, and I also said that I'll sum it up from 3 to infinity. The reason I've already pointed out above. So if we expand this, then we will be getting something like this. The first term will be a3 x3 a4 x4. I'm just putting the value of 3 in the place of n on the first term, right? And I'm just increasing the value to get the different terms. So this is what I'm getting, a5 x5 dot dot dot. Second term I'm getting as this, 6 a2 x3. Again I'm putting n equal to 3 4 5 6. I'm getting the values of a suffix 2 etc etc. So a3 x4 plus a4 x5 plus dot dot dot, and then we are getting 11 a1 x cube a2 x4 a3 x5 dot dot dot, and we are also getting minus 6 minus 6 a0 x cube plus a1 x4 plus a2 x5 plus dot dot dot, and this is equal to 0. So just substitute the value of n from 3 to infinity and you will get the coefficients of these terms. So now what do we need to do? We will need to compare it with gx. So gx is equal to a0, a1x, a2x, a2x square, a3x cube, and so on. Right? So we will, for the first term, what do we get? Let us see what the first term. Now for the first term, if you see, we have a3 x3, a4 x4, a5 x5. So it is of this format, a3 x3, a4 x4, a5 x5, of this format. So these few terms need to go to the left side. These few terms need to go to the left side. Right? So what we'll say that for the first term, we will be writing that a3 x3, a4 x4, a5 x5 is equal to my gx minus the terms that are redundant on the right side, we will bring it to the left side, minus a2 x square. So this is what will the removing of the first three terms do, and that's pretty much what the first term will be for us. Right? So the first term is like looking like this. For the second term, let me move to the next page. For the second term, our second term is of this format. Okay, let me put that a2 x cube. This is my second term. a2 x cube, a3 x4, a4 x5. a4 x5, and this goes on. So this is my second term. Now if I compare it with gx, which is a0 a1x plus a2x square plus a3x cube plus a4 x4. Now I see here two interesting things. One, a2 x3. Now can a2 be with x3? a2 can be only with x2. So 1x is extra here. Here also 1x is extra. a3 x3, we have a3 x4. Why I am saying that? See, a3 x3, a4 x4. So when I compare it with my generating function, 1x is extra everywhere, isn't it? So we have to remove that 1x, which means that we'll have to factor out that x. Let's just factor out that x. So from here, if we factor out x, right, then we will get this is equal to x into a2 x2 plus a3 x3 plus a4 x4 plus, now we have something which is in the generating equation format. So this is my generating function format, right? So that is what we have got. But the format is okay, but this part of this problem is actually coming from here. So we have to take this part to the left, right? So that's what we will do now. Therefore we will say that okay, so let me put this here. So gx minus a0 minus a1x is equal to a2x square plus a3x cube plus a4 x4. Right? So this is what I did. I just took these two terms from here and put it to the left side. Now I can see that these two terms are matching. This particular term and this particular term are matching. Right? So that is what I have concluded, that okay, if this is the case, then can I write my term which is so I'll take this now. So can I say that a2 x square, or rather my second term, whichever was that second term, it's actually equal to this only, but then let me put it this way. So a2 x cube yeah, so can I therefore write this particular term? What I'll just bring in this term here. Okay, I'm just bringing in this term here. So I'm saying my a2 x cube plus a3 x4 plus a4x5, whatever that is equal to what? We just factored that out, right? We said factor out that x from here. So it is x multiplied by, this is what? This is gx minus this. So let me, I think I skipped one step. If I bring that step back, then probably it will be easier for you to understand. Let me bring that step back for you. Okay, so this is going to look like this. Yeah, so it's going to look like this, that I will bring this here. Let me remove this, it will create confusion unnecessarily. So what I am doing here is I am taking this and I am writing this as x multiplied by a square x square x. What is that? That is equal to gx minus a naught minus x, right? So this is gx minus a naught minus a1x, and that is what my first term is actually equal to. So my first term is actually equal to x multiplied by gx minus a naught minus a1x, because this I have substituted here, right? Because this is equal to this, so I have substituted gx there. So my first term is equal to this. That means that this entire thing, now we can say this entire thing, that's the step I was jumping, a2x cube plus a3x4 plus a4x5 is actually equal to or rather dot 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 right, is actually equal to x multiplied by gx minus a naught minus a1x, right? So that's my first term. So this is how my first term gets, or rather the second term. We were talking about the second term here, right? So this is my second term. Let me write it fully. So that's my second term output in terms of the generating function. So this is my second term. So what is my third term here? Let me see what is my third term. So let's write the third term on this side. Right, so the third term that we are going to get is looking like this: a1 x cube plus a2 x4 a3 x5 plus dot dot dot. So what is not right? If I compare it with gx, a0 plus a1x plus a2x square a3x cube, what is not right? Let us see. So a1 goes with what? A1 goes with a single x, so 2 x's are extra. A2 goes with x square, 2 x's are extra. So we have to factor out x square. So factor out x square. If we do that, this term becomes equal to x square a1x a2x square a3x cube, etc., etc. So this becomes x square multiplied by, now this a1x starts from here, right? This is what this is. These two are the same. So this is actually equal to what? Gx minus a naught. So let me write directly here. I hope you will understand gx minus a naught. Right? So that's what my term will look like. So I can therefore write that my third term is equal to x square into gx minus a naught. That's my third term. And my fourth term, if you see, my fourth term is like this: a0 x cube plus a1 x4 plus a2 x5 plus dot dot dot. So here what is wrong? Let's see. My gx is equal to a0 a1x a2x square a3x cube and so on. So what do we see as a discrepancy? Let's figure out. a0 comes with x0, so 3 x's are extra. a1 comes with x4, a1 should come with x1, so 3 x's are extra. So we have to factor out x cube. So factor out x cube, and that makes it equal to x cube a0 a1x a2x square, etc. And you know that this is this. right? Which means we got gx here, right? So which means we got gx here. So therefore we can write x cube into gx, right? So that becomes my fourth term. My fourth term therefore can be written as x cube into gx. Now if we put all of this into the final equation, then we will get something like this. We are putting all of that into the final equation. We are getting gx minus a naught. This was the first term we had found out. Minus a2x square. That was the first term we found out. Minus 6x multiplied by gx minus a naught minus a1x. This was the second term we found out. If you see here, our equation that we had to solve was this. This is our first term, minus 6 for the second term, plus 11 for the third term, minus 6 for the fourth term, right? So that's what we are doing here. And then we have plus 11 for the third term. Whatever we had solved was 11x square gx minus a naught. Then we have minus of 6x cube gx. This is equal to 0. Now we already know what the values of a naught, a1, etc. are, right? So if you see here, a naught is 1, a1 is minus 1, a2 is minus 1. So if we substitute these values, so we'll say substituting a naught equal to 1, a1 equal to minus 1, a2 equal to 1, we will get gx minus 1 plus x minus x square minus 6x gx minus 1 plus x plus 11x square gx minus 1 minus 6x cube minus 6x cube gx equal to 0. If we expand this, we will get gx minus 1 plus x minus x square minus 6x gx plus 6x minus 6x square plus 11x square gx minus 11x square minus 6x cube gx equal to 0, right? So simplification, it will take some manual labor, I understand. If we group the gx's, then we get gx 1 minus 6x plus 11x square minus 6x cube, that plus minus 1 plus 7x minus 18x square is equal to 0, which actually implies that if I take things to the right side, I will be getting this. I should be getting this, that gx will be equal to 1 minus 7x plus 18x square divided by 1 minus 6x plus 11x square minus 6x cube. So this is what I'll get. So if I factor the denominator, and then you can do it by the division method, because this has 3 factors. So you have done this in your class 11. You can do it by the division method to find out the 3 factors. I'll just quickly write them down. So gx will be equal to 1 minus 7x plus 18x square by 1 minus x, 1 minus 2x, and then 1 minus 3x. So you need to take 1 minus x and divide the entire equation polynomial. You will get the output as a quadratic polynomial, which you can middle term factorize. That's how the division method was, if you remember from your class 12 days or 11 days. So now we can convert this into a partial fraction. So we will say this is, assumption is a by 1 minus x plus b by 1 minus 2x plus c by 1 minus 3x. So if we take the LCM, then we are going to get 1 minus 7x plus 18, 1 minus 7x plus 18 x square is equal to a into 1 minus 2x 1 minus 3x plus b into 1 minus x 1 minus 3x. I'm just doing the LCM and multiplying the corresponding terms. C 1 minus x 1 minus 2x. Right, so now if I expand and compare and then collect the coefficients, then I will get something like this: 1 minus 7x plus 18x square is equal to a plus b plus c plus 5 minus 5a minus 4b minus 3c x plus 6a plus 3b plus 2c x square. This is what you will get. And then if you compare it with the left side in terms of the coefficients of x square and 1, then you will see that a plus b plus c is equal to 1. Another equation will come as minus 5a minus 4b minus 3c equal to minus 7. Another equation will come as 6a plus 3b plus 2c equal to 18. So if you solve this, then you will get your a is equal to 6, b equal to minus 8 and c equal to 3. This will be your solution. So you put them here. You will get gx as equal to 6 by 1 minus x, 8 by 1 minus 2x, 3 by 1 minus 3x. So the same funda as we used earlier, 6 by 1 minus x is actually sigma of n equal to 0 to infinity x to the power of n from the earlier table, right? The same thing. It's actually similar to the last problem. So I'm not showing you the table again. And then we have 1 by 1 minus 2x as sigma of n equal to 0 to infinity 2 to the power n x to the power n, just similar to the last problem. And then we also have 3 here, 1 minus 3x. So this is going to be looking like, and then we have this as 6, this as 8, right? And this as 3, sigma of n equal to 0 to infinity of 3 to the power of n x to the power of n, just similar to the last problem. So I hope you can understand this part. And if I therefore do the summation here, this will look like sigma n equal to 0 to infinity, and then we can take 6 minus, is there a minus? Okay, b is minus, so this should have been a minus. B is minus, right? So we found b as minus 8. So this should have been a minus here. If this is a minus here, then this is also a minus here. So we'll get 6 minus 8, then 2 to the power of n plus 3 into 3 to the power of 3n. 3 to the power of n. And then we will also be taking x to the power of n common. So that is going to be your answer. Now if you compare the coefficients, then this is your an. This is of the format of an xn, right? So which means that an is equal to 6 minus 8, 2 to the power of n plus 3 into 3 to the power of n. This is the solution of the recurrence relation in the format of the generating function without using any recursive call. And if we compare this to the time complexity, we can write an or tn, whatever we want to call it. This will be theta of the dominant term. Dominant term is 3 to the power of n. So that is your answer of the time complexity. Yes, I know it's pretty long, pretty lengthy, but it's a mechanical way of finding things. If you know one way, you can just do it, and this is a very scoring thing. If you can do it correctly, you will get all the 15 marks, full marks. Sometimes it comes for 10 marks, sometimes for 15 marks. So let's do the last problem that we wanted to discuss in terms of the previous year questions that typically is asked. And this is again a similar problem. Mostly it will be a lengthy solution again, but let's attempt it. Now what we are doing is we will multiply this similar to the last time. We will multiply it with x to the power of n, and then sum it up. I understand, but then sum it up till what? And sum from what to what, right? So I told you take the lowest power n minus 2, and what is here? A0 is 0, right? So the A0 is given A1. Sometimes A1 could be given, then n minus 2 will be 1. Here A0 is given, take the lowest power, lowest suffix, which implies n equal to 2. So we will say 2 to infinity here. And when we do this, we will get sigma n equal to 2 to infinity an xn minus 7 sigma n equal to 2 to infinity an minus 1 xn plus 10 sigma n equal to 2 to infinity an minus 2 xn equal to 0. So if we expand this, right, similar to last stuff that we did, unless it is different, I will just keep on solving it mechanically because I've already explained it how to do it or why am I doing it. So a2x square, I'm expanding this, and then a3x cube, a4x4 and so on, minus 7 a1x square, a2x cube, a3x4 and so on. Then we have plus (10) a0x square, a1x cube, a2x4 plus equal to 0, right? So that's on expansion. Now we will have to compare the first term. So I will be comparing the first term, which is a2x square, a3x cube, a4x4 with the comparison will be with gx a0, a1x, a2x square, a3x cube, a4x4 dot dot dot. So as you can see, this term is exactly the same from here. So can I write this term as gx minus a0 a1x? I can write this at that. Now you are understanding this. So instead of writing those steps again, I can directly say that my this term, first term, is equal to gx minus a0 minus a1x, right? I can do that. My second term is a1x square, a2x cube, a3x4. So I already see that a1x square is not correct because it is a1, it should be x. It is a2, it should be x cube. So one x is extra. So I will say that I will factor out x, which means x into a1x, a2x square, a3x3 plus dot dot dot. Now if I compare it with my gx, so if I compare this with gx equal to a0, a1x, a2x square dot dot dot, then I will see that my a1x, which is here, matches with a1x, which is here. So this matches with this. So it should be x, gx minus a0 should be something that I should put here, right? So I should be putting something like this, that this is x into gx minus a0. Right, so I hope you are understanding this, gx minus a0. is what my second term will be equal to. So this is my first term, this is my second term, and we are moving into our third term. So our third term will be a naught x square, a1 x cube, a2 x4, and then you can of course imagine that two x's are extra here, right? So here you have a naught x0, you should have had, you have x2, a1 x1, you should have had a1 x1, but you have a1 x3, two x's are extra, so factor out that x square. So then you will get a naught, a1x, a2x square, and so on. And this is when compared with gx equal to a naught plus a1x plus a2x square, right? So you will see that this one is same as gx, right? So can I therefore put this gx here? I can definitely put this gx here, right? So let me put that there. So this becomes equal to x square gx. So that is my third term. Now I can easily substitute it into this main equation. This main equation was looking like this. So you have a 7 coefficient here, 7 multiplier here, you have a 10 multiplier here, and you don't have any multiplier here. So let me put this into that equation. So when I put this into the equation, it looks like this: gx minus a naught minus a1x, that's my first term. Then we had the 7 multiplier with x gx minus a naught. Then we had the 10 multiplier with x square gx equal to 0. Now if we substitute the initial value was given as a naught equal to 10, a1 equal to 41. That was the initial value given in the question. If we do that, then we will get gx minus 10 minus 41x minus 7x gx minus 10 plus 10 x square gx equal to 0. So if we solve this and put all the gx terms together, then we will see that it comes to gx 1 minus 7x plus 10x square plus minus 10 plus 29x that is equal to 0, and therefore this becomes equal to 10 minus 29x divided by 1 minus 7x plus 10x square. We can middle term this out very easily, and we will get this as 10 minus 29x, 1 minus 5x, and 1 minus 2x. And we can of course write it as a partial fraction now as 1 minus 5x plus b into 1 minus 2x. So if we do the LCM and cancel out things, then we will get 10 minus 29x is equal to a into 1 minus 2x plus b into 1 minus 5x. And if we expand this and then group terms together, then we will get 10 minus 29x is equal to a plus b minus 2a minus 5b into x. So if we compare the coefficients, then a plus b is equal to 10 and minus 2a minus 5b is equal to minus 29, right? And therefore if we solve this, then we'll get a equal to 7, just simple linear equation in two variables. This is what you will get. So your gx, the generating function, will now look like 1 minus 5x plus 3 by 1 minus 2x, and this is, as you know, sigma of from the previous table. We have already seen this, n equal to 0 to infinity, and it will be 5 to the power n x to the power of n because it is 1 minus 5x, 1 by 1 minus 5x, and this is 3 into 1 by 1 minus 2x, so which will be sigma of n equal to 0 to infinity of 2 to the power of n x to the power of n. So if I aggregate the sigmas together then I am going to get n equal to 0 to infinity of 7 multiplied by 5 to the power of n plus 3 multiplied by 2 to the power of n and the whole to the power of x to the power of n. If I take x to the power of n common, which means my an is equal to 7 multiplied by 5 to the power n plus 3 multiplied by 2 to the power of n, because this is of the format of this is of the format of a to the power of n x to the power of n an x to the power of n. So I am taking an as 7 into 5n plus 3 into 2n, which means that my an or my tn from a time complexity asymptotic perspective can be made equal to theta of 5 to the power of n. That is my answer from a time complexity perspective. So this is how you will solve generating functions to find out the time complexity of any recurrence relation, and that was the topic of today's lecture. So I hope you have had an understanding. I know it is a lengthy process, but there's nothing much that you can do about it. These set of steps have to be done for each and every problem, and as I said, it's pretty scoring in nature, so please make an attempt to learn this and have those marks in case these questions comes. Thank you till the time we meet next.